Okay, folks. Um, Welcome to my home. All right. Today, I actually asked. I did a Twitter poll yesterday about what I should talk about today, and it was a really close race. There were three topics. One was all about side channels. That's what won. That's what I'm going to talk about today. Another was a deep dive into blockchain, and what was the third? I can't even remember what the third was. But they were all like 33%, 33%, 33%, almost the whole way. And several times they were exactly even though there were dozens or hundreds of votes. But side channels won out, which I'm happy about because it's one of my favorite topics to talk about. A lot of people have heard of side channels, but they're kind of mystifying and scary things. So I'm going to try and demystify them and really dig in and get to the point where we can understand them. As ever, if people have questions along the way, just go for it. Just throw them in and I'll either answer them in real time or I'll get to them all at the end as well. I'll do a scan when I'm done. Everything I'm going through, it's kind of off the cuff, but I do have somewhat of an outline, so hopefully I'll get through all of that in some semblance of order that will cover all this material. People have been asking if I'm going to put all these on YouTube. I am. I've set up a channel and I'm working on it. I just have to load the old videos into an editor to cut out the first minute or two where it's just waiting for the stream to begin and so on. So that'll be coming too. No worries. All right. With that, let's get going. I'm going to switch to the document view for most of this, so I can use my document camera and write notes as we go. And I've got some papers to show you, and we'll probably switch to code at a certain point too. And we'll see how we do. Oh, there we go. The other one was about functional C programming. Another topic dear to my heart, which we'll cover some other day. All right, let's get going on side channels. So side channels are, way simpler than they seem. They're a scary topic that can come up in a security context, and you see in academic research, and the last 10 or 20 years of emerging cryptographic research. A lot of it's been on side channels and how they can be used to exploit systems. I'm going to cover some of that. We're going to work up to understanding what's going on there. But as I said, side channels are actually really simple, and I'm hoping that I'm going to give you a version of side channels that like us mortals can all just understand and follow and learn from. And my goal here is, like, if you watch this video, or follow along, you're going to end up in like the top % of people on Earth who know things about side channels, because they really are that simple, it's not as hard as it seems to follow things along. So side channels, let's construct something of like a security theater or some place where we want to run a secure system. So let's take a really simple example, the very classic example of we've got Alice and Bob, and they want to communicate to another, and they encrypt all the communications between them, right? Everything here is encrypted, and if you could somehow break this encryption system, if there was some kind of bug in the encryption algorithm or bug in the encryption software that led to memory disclosure or something like that, right? That's just like a break of the system that opens up the information that we're encrypting or trying to protect or whatever, right? Side channels are kind of like a cleverer way of trying to come at that, right? They're trying to use things. So let's say we've got Eve, who has eyes on this data. We call her Eve because she's an eavesdropper, right? And she can see all this data going by, right? And what are things that she can see, right, that are basically public? Or let's assume that she's, got $1 billion submarine and is tapping cables or something. And what are things that Eve can see, even though this information is encrypted and protected and secure in air quotes, that reveal the contents of this information, right? And so the way we're going to think about side channels, we're going to think about it through this kind of lens of a threat model of like, what can an actor with this kind of access see, right? Now there are other side channel threat models that we'll cover later in a bit, like what if Eve is running code on the same physical hardware as like Alice or Bob, and we'll cover that a bit later. But you know, to generalize at this point, the idea is Eve has some kind of visibility of the activity between these parties and wants to guess at what's going on, right? So let's take an easy case, like let's say Alice and Bob, they're just sending information back and forth that's encrypted. What can Eve see? Well, straight away, right, Eve can see how much data is going back and forth, right? In general, Eve can see the size of any particular data fragments, right? If you're using an encryption protocol like TLS or IPsec or WireGuard, any of these things, you know, Eve, even though the traffic is completely encrypted, can still see, well, how much is kind of going around, right? And Eve can also do timing, right? Eve can see, you know, when this message goes across, how long does a reply take, and so on, right? Just use her own clock to measure that, and straight away, right? Just this level of access of being able to see data and time things leads to some like incredibly cool side channels. My favorite side channel of all time actually really takes no cryptographic understanding or anything like that. You can read about it in this paper if you want to go find it. But it's one of my favorite side channels because it's so simple, it's so effective, and I've actually seen this several times when I've done security reviews for customers and teams and so on, right? And it's really, really simple. What it is, you know, imagine Alice and Bob are sending encrypted voice communications back and forth, right? So they're using some kind of audio codec to encode their speech, and it's going back and forth, right? Well, if you implement this naively, and this is at the like speech layer, this is not even at the like cryptographic layer, right? If you implement this naively using like a variable bit rate encoding, or you have what's called silent suppression, so the codec saves bandwidth, and you know, whenever nobody's speaking, doesn't bother to send anything, just sends these little messages that say, you know, it's silent right now, so the bandwidth can be conserved, and the other end actually can generate like fake silence, like some room noise, so it doesn't feel like a dead line. But there's protocols that do this. But just that, right? Eve can actually observe, and just by this paper that they found, right? Just by looking at the silences, not even looking at the you know, compression rate of the audio or anything, just looking where the silences were, could decode like a huge percentage of speech, right? Just by looking at where the silences land between the words, they could guess how long those words were, right? And build this probabilistic model of like, well, this long a word followed by this long a word followed by this long a word, and so on, and take a really good guess at what the speech was, right? Scary, right? So, and I want to emphasize, right? Like some developer, you know, they went and used a variable bitrate codec, they glued it together, they ran it over an encrypted protocol, they were doing everything right? And it still led to an issue where somebody just looking at the traffic could actually tell what the parties were speaking, which is kind of mind-blowing, and it's kind of cool. Sometimes in cryptography we have this idea, you know, it kind of started with the concept of AEAD mode, which is like this mode that's supposed to protect developers from themselves. You know, we can come up with cryptographic abstractions that's just gonna like protect everybody magically, but like side channels and papers like this show you a really deep end-to-end understanding of the whole system is necessary, and also approaching the system from the mindset of an attacker, right, and red teaming it is necessary before you're ever really gonna like convince yourself and find all those things. To beat a side channel like that, for what it's worth, you know, what you try to do is, well, don't use a variable bit rate encoding. You know, try to send traffic at a constant rate all the time, and don't use silent suppression. Send traffic even when there are gaps between the words and so on, right? And then you'll do it. And you know, modern good you know, VoIP clients and things you can use like that tend to get that right. So that's a really, really simple example. Just want to start there, right? Doesn't require any particular understanding. Another example of this, kind of, which came out a long time ago, I think I have the paper here somewhere, is keystroke timing, right? So you imagine you're using the SSH protocol, and you're logged into a machine, right? And you're just typing away, and it's going over the encrypted SSH protocol. SSH is a really well-designed protocol. It's super good encryption. They know what they're doing, right? But if your individual keystrokes, one by one, right, are making it over the wire, even encrypted form, someone can just measure, right, the timing of those keystrokes. And again, they can build this probabilistic model. It's like, well, this timing between these two keystrokes, that tends to be like an A followed by an S. They're really close to each other, so that's quick. But this one could be like an A followed by a K because those aren't so close, and so on, right? And work backwards and like build that model up and up a bit, and eventually figure out, okay, it was probably this letter followed by this letter followed by this letter followed by this letter, and figure out what you're typing, right? And for something like a password that you type in, you know, once a day maybe, or maybe even more often, you know, Eve gets several cracks at this, right? Can just monitor a few times and try to really refine this and make better and better guesses about like what's going on and what keys you're hitting, right? And eventually figure out those keys and crack your password, right? And again, the information's all perfectly encrypted, right? And it's just going around exactly as you'd expect. And what we're doing here, what the attacker's doing, is exploiting, you know, just intrinsic properties that are exposed by the virtue of like how humans type and so on, right? Now the fix in the SSH protocol and how they avoid this issue, right, is anytime you're doing secret input, like a password, you know, a terminal or a terminal application is supposed to switch to a line buffered mode, right? So they tell your terminal, look, don't send me any data until the whole line is done, they've hit return, and then send me the whole thing in one go, right? So that the keystrokes aren't exposed over the wire, right? But that's interesting. And sometimes you can come across these, you know, applications that people have built that don't know this and don't understand this rule and do their own password input, where they, you know, use a library like Curses or something like that, and they like, you know, when you press a letter, they echo an asterisk and so on, right? Because they want to be cool and fancy, and they're actually getting pretty bad security because they're going backwards and they're exposing the keystrokes. But the biggest thing I want you to take from this, right, is like these are strong examples, strong practical examples of what a side channel is, right? Eve is just looking at some information that's totally public as far as our model is concerned, right? Like we have to assume because we're encrypting communications, we have to assume that the encrypted communications are somewhat visible. You know, maybe they're using shared Wi-Fi, maybe it's going over a link that could be tapped or whatever, right? But Eve's just looking at that information and can learn things like speech or passwords and so on, which is kind of mind-blowing, right? And by the way, you know, these issues, which don't get too much academic attention because, you know, in the academic field, those papers are long published. There's not much to refine there. You know, it doesn't mean that developers don't make these mistakes over and over, and that you can't find applications and protocols and implementations that are vulnerable to these things, which is kind of staggering. We don't talk about them nearly enough, in my opinion. All right, so let's work up from there, right? So we started by looking at like basically data traffic rates and some trivial timing, and we were able to figure out speech and keystrokes. Well, what more can we do, right? Well, obviously Eve can see the length of data that is going by, so straight away you can start to do things like content fingerprinting, right? So, you know, when Alice sends Bob a request, let's say Bob's the web server and Alice is the browser, you know, she's going to send a HTTP request, which has a URL in it, and then Bob's going to send a response, right? And Eve can look at the size of both of those things, right? And she can see, hey, Alice just sent a request, it was this long. Bob just sent a response, it was this long. And put those together to try to do some content fingerprinting. So, you know, a simple example of that, and there have been papers published around this, is, you know, hey, go profile every single web page and resource on, say, Wikipedia, and build this database of, you know, how long the URLs are and how long the responses are, and and you can pivot from there, because you can also include like any CSS they load, any JavaScript they load, anything like that, to build this overall content size fingerprint of a resource, right? And you build that database yourself, kind of offline. So Eve maybe just keeps that database of all these things, right? And then she matches Alice's request and response against that, and can make a really good guess at what page Alice is actually looking at, right? Which again, super practical. There have been papers published on this, not just on things like Wikipedia or other websites that are mostly static, but also on things like there's a great paper that did this on maps tiles. So when you're looking at a map location in an online maps application, it could tell what location you were actually looking at, because it had profiled the sizes of all the maps tiles, right? Super cool. Or another one that did it on video streaming, right? So it looked at the encoded parts of the video and could tell, even though all this was encrypted, what video someone was watching, right? Which is pretty cool. There are even commercial products that can do this kind of stuff. There are vendors who have content fingerprinting and traffic analysis fingerprinting that's designed to kind of make good guesses of what people are using, even over encrypted connectivity. Typically it's to like block video streaming, because maybe like a hotel doesn't want you sucking all their bandwidth and somewhere where they don't have a lot of it, or things like that. So it's mostly not about the creepy things of like actually trying to find the individual pieces of content you're looking at. But you could certainly extend that kind of approach to do something like that. It's super cool. I'll talk in a bit about how we can mitigate some of this stuff. But for now, I just kind of want to excite you with some crazy ideas or crazy examples of just how effective side channels are. They're way underrated in my opinion, and an underappreciated topic of security research. All right, so we've done data rate, we've done data length. I want to extend that a bit more. I don't have a paper to show you, because when they revealed this attack, they did it in presentation form. But I want to talk about crime for a bit. You can't see that, can you? Which was an unbelievably cool piece of research that was put out quite a while ago now, and then extended with other things called breach and more. But these are compression attacks, and they build upon the examples we just did, where we're looking at like data sizes and data length, but they extend that by introducing a shared aspect, right? And I'll that's going to be important. We're going to see more examples of that later. But the way crime works is super cool, right? So we first need to understand how compression works at a super high level, right? Before we can kind of understand crime. So let's say you've got some piece of data, right? And you want to compress it, right? My high level model of a compression algorithm is it takes that data and it outputs a smaller amount of data, right? And the way it does that, right? The magic of compression is that it identifies commonalities over here, right? And anything that's in common, it can literally compress them. There's all sorts of compression algorithms and compression techniques, but they essentially all have that in common, right? And typically a compression algorithm will process this input in blocks, right? So let's say 8K or something like that. And it'll go over that 8K and it'll go, okay, I'm going to process this 8K of data now, and I'm going to find any commonalities in that 8K of data and produce a smaller amount of data, maybe 1K, right? And that 1K is going to comprise of a compression table, like here's references for all the little things that are in common, and then kind of like iterations of those things, right? And the way crime works, right, is suppose an attacker or someone who comes along can control some of the data that's in here, right? You know, like I'm just going to put a piece here. Some of the data that's in here and wants to know some of the other data that's in here, right? Well, through trial and error, they can figure it out if they can observe the size. Because if they put a piece of data in that matches another piece down here, like if they're the same, then the overall size won't go up, right? Really, because it won't go up by much, at least, because they'll both be compressed to the same entries, right? And you kind of think this is innocuous because you think, well, but how can I find an example where like an attacker can generate input that's going to end up in the same output as sensitive data and so on? But this was the really, really clever part of the crime attack, right? They figured out ways of doing that. They found examples where, you could generate URLs that you would, partially be able to control some of the content and then give it to somebody and then watch what they do. And then if their output overlaps with your controlled input, you'd be able to measure it. I don't want to walk through their example because I think it's a little too complicated for this one, but I'll give you another example which I think is easier, right? Imagine every few minutes you're backing up your email inbox, right? And let's imagine that as part of your email inbox, you gzip it, right? So every 5 minutes you gzip your inbox and you back it up. Totally reasonable way to build a mailbox backup protocol, right? There's systems that work like that. Now let's say you've got an email in there which might have a sensitive string in it, right? Attack at dawn is the classic case from the cryptographic literature, right? Like a World War II example. And I want to tell, well, do you have attack at dawn in your email box, right? So I'll send you an email and I'll say, so buried in my email, maybe not even visible, like maybe I'll use clever CSS tricks and so on so it's not visible. I'll have attack at dawn in my email, right? And now I know it's in your inbox. And now I look at the next backup and I go, well, when they do that backup, what did the overall size go up by? Did it go up by as much as I would expect if the string is there or it isn't there, right? It's a bit of a contrived example, but it's easier to follow. The HTTP examples get more complicated. But that's just one example, right? And so to defeat these attacks, right, you actually have to have, separation of the compression layer and compress each piece of input individually, right? And not share that compression context against anything that might be untrusted input, that also with anything that might be sensitive, right? So again, to get over side channels like this, you have to be thinking at the application layer. Anyway, that's crime. That's an example of a compression side channel. Oh, one thing I should say too, right? There's two ways a potential attacker could kind of get at this with a side channel. One is that the attacker could literally see the size of the compressed data because maybe they can see the data going off to the server. The other is they can time it, right? In general, these operations take an amount of time that's proportional to the compression ratio and so on too, right? So that's a little bit of an important concept for later, that we can use time as well. All right. Now, we're going to get to the scary section for me because I'm going to try to actually code and do a live demo. Because so far, everything we've covered, I hope, doesn't require understanding of code or programming or anything like that. And you're not really going to need that either to follow what I'm about to get into. But they're just conceptually, really simple, hopefully, easy to follow examples of how these weird side effects of data handling go on. Someone just asked, if I encrypt the data, then the compression attack won't work. That is completely true. If you encrypt the data and a compression attack won't work, but also compression won't work. You can't compress random data. It's just one of those foundational things of information theory. If there's no pattern, there's not much you can do. But if you compress before and then encrypt, that's when you get into trouble. That's when you have to be careful to watch the compression ratios. All right, I'm going to try to switch views to the code view. And we're going to do our first and simplest example of a code level side channel and what's going on, right? So let me make the code font way bigger before I try to switch the screens over. So the code example you're going to see is in Rust. All right, hopefully you can see this. If this is not readable on your screens, let me know and I'll make the font size bigger. Okay, I'm getting immediate feedback. All right, let's try that. How's that? Bigger? All right, we'll go even bigger. I'm just going to err on the side of being too big. And we'll just walk through it line by line, and that'll be fine. So, we're going to crack a password using a side channel, right? And this kind of vulnerability and issue, it's kind of like side channel 101, and a lot of side channel explainers start with this example. And this is a regularly implemented side channel. Like, this happens all the time. I have found examples of this. It can happen when developers are checking passwords, and it can happen when developers are just doing things like checking, still a bit small, like checking whether two Macs are equal, like two HMAC values, right? So even when you're doing fancy cryptography, you can make these mistakes. All right, that is about as big as I can make it. All right, looks good now. All right, thank you. So this is in Rust. Rust actually makes it hard to write insecure code and likes to give you abstractions that protect you from yourself. So I had to fight Rust to even kind of implement this. So this is kind of in some non-idiomatic Rust. This is not really how you do a password comparison or compare strings in Rust. It's a very natural way to do it in many other programming languages, especially C and so on. But I still wanted to use Rust because Rust is cool. But anyway, I'll walk through what's going on here. So we've implemented a really simple password checker. We're just going to compare whether an input is the same as a password, right? And so this is the actual check function, right? Where we take the password as input, we take an input as input. If they're not the same length, obviously bail, right? They're not equal. If they are the same length, then we're just going to go through every character in the password and every character in the input, and we're going to see if they're equal. If they're not equal, bail. If they were all equal, we'll get to the end, return true. Very easy, natural way to write a string comparison. This is basically what most string comparisons are doing under the hood. They all boil down to assembly instructions that can actually do this pretty natively in a CPU. If you look at what memcomp is doing, they can do this all the way down, although they'll do it word by word rather than character by character just to be more optimal. But the principles are all the same, right? This has a side channel. This is insecure, right? This very natural way that you would write it. I can crack your password, and we're going to do that, right? And the reason why is, right, okay, suppose I want to try to guess your password. What I'll do is I'll feed an input, right? Now, if my input is too short or way too long, I'll bail super fast, right? And I can measure how long that takes. And so I can sweep through a bunch of reasonable values for password length, right? And then just measure how long each one of them takes. And some value along that way, right, is going to take longer than any other value, because it's going to get past, basically past this branch here, and it's finally going to get to this line, right? And that's going to take slightly longer, and I can just measure that. Now I know your password length, right? For sure. Okay, now I know your password length. What do I do? All right, well, I'm going to start with a password that basically, I'm just going to focus on the very first letter of your password, and I'm going to try every single letter there is, every typable character, right? And one of those values is going to take slightly longer than the rest because basically 99% of those values are going to fail this check here, and they're going to bail. But one isn't, right? The right one, and it's going to get through to the next iteration of the loop. Now the next one will probably fail because I don't know the next letter and so on. But now I just by measuring things got that first letter of your password. Now I know the first letter of your password. Every attempt I do from now on, I'm going to start with that first letter. And I'm going to just do the same game on the second letter. Right? And so on and so forth. And I'll crack your password. And I've actually written this here in Rust just to show it to you. Right? So I'll walk through how this cracker works. I've got this, this is a recursive function, this crack function. And basically I start off with a constant array of every typable character, right? So this is all the valid guess words. For every single one of these characters, I'm going to make 1,001 measurements, right? And then I'm going to keep the medians of all those measurements. So the median is the 50th percentile. So that's the value where basically 500 measurements are higher, 500 measurements are lower. I'm going to pick that number in the middle just as a representative statistic of the overall time of our average. It's not the mean average, it's the median average. It's less influenced by noise. But I'm going to use that to measure. And like I said, this is recursive. So this is my terminator, which is when I finally get to the point where the known string is the full length of my password, just return, right? So this is how I terminate my recursive function. The way this starts, I call crack with an empty string. I know nothing. And then every time I get a new character, I add it to known and then call myself again recursively all the way until I have all of the letters, right? So we're just using recursion as our iterator. And it's really simple. You know, for every character, I'm going to add it to my known, right? So I'm gonna produce a guess word, and I'm gonna run 1,001 measurements. I'm gonna run check 1,001 times, and I'm gonna measure the time it took every single time. I'm gonna sort those measurements. I'm gonna take the 500 value, right? So that's the median. And I'm gonna store that in medians, right? And then at the end, I'm gonna go through all the characters' medians. I'm gonna figure out which one was the max, which one took the longest, and that's my guess, right? That's my strong guess for what I think that character is. And then I'm going to recurse and we're good, right? So this is the recursion and we're going. So this takes a password as input and then lets you try to crack it, right? So let's do let me in. Sorry, can't type. So I got the first 4 letters, pretty good there. And yeah, it's not getting much better. So normally this takes me about 10 attempts. That got the first 5 letters and the letter at the end. So I still have to run this a bunch of times, but it will get the exact check each time. Every time you run it, you're getting really high confidence at this point, right? That like the first 3 letters are definitely let, right? This might not get me a perfect result with Twitch running. So what's going on here, right, is the first few letters, it's really, really good at guessing. And the letters after that, it's not as good as guessing. And what's going on is when I run this command, those first letters, the timings are super consistent because the scheduler in the Mac OS kernel, I'm running on a Mac, is giving the Rust program like basically exclusive access to the CPU for a while, right? And so the timings are all pretty much perfect. If I went to the trouble and like wrote this program to basically run on a dedicated CPU core with nothing else scheduled on that core, it would give me perfect answers every single time. But it's really just the noise of the system, like other things being scheduled and coming in that are ruining those later guesses. But you can still tell, like you can get a feel here that like I'm gonna get this password. Like I'm getting really high confidence about what it is, and I can just go check each attempt, you know, and I can figure out eventually what the password is. And this was just with like 1,000 measurements for each character, right? Now this kind of noise, it's harder when you're dealing with remote systems, right? So if you're trying to do this against something over the network, you got to subtract all the network noise and so on. And the usual trick for that is just do even more measurements, right? And so by the time you're doing millions, billions of measurements, you know, you can eventually figure this stuff out. And that tends to be way more efficient than brute forcing these days. You know, if there's one of these side channels there, it's more efficient to use it than not. Like than to just all right. So we're gonna fix this, right? So we know there's a side channel in it. How do you avoid a side channel like this, right? So this problem comes up a lot in cryptographic code, and actually the art of writing some difficult to write cryptographic code is basically everything I'm about to show you. Like this is what we spend a lot of time getting right. So to defeat this kind of side channel, right? We can't really do anything that's in purport, you know, that's just gonna stop when something is wrong, right? Like we can't just bail early like this. So we have to take a very different approach. So the usual approach is kind of ugly, but I'm gonna do it anyway. We're gonna follow along, which is to basically do some clever bitwise operations. And so let's see. So we're going to add this 8-bit integer, unsigned integer, or, which is going to represent kind of a return value. We want this thing to be 0. We want it to always be 0. So just focus on that for a second. And instead of this branch here where we check if A is equal to B, what we do is, just looking at my notes. So I'm going to write some ugly code and then I'll explain it. B as U8. All right. So here's what's going on. So we start off with OR 0. That's easy, right? And what we then do is we XOR XOR exclusive OR the values of A and B. So A and B are the characters that we're iterating over. And the important thing here, right, is the way the truth tables for XOR work out. Let me switch back to my document view just for a second. I've gotten this wrong before, so let's see. So A and B and A XOR B. So if we look at the truth table for these things, right, it's an exclusive OR. So let me get all the values out first. So the trick is, what is the trick? So when it's 0 and 0, the output is 0, right? Like because neither of these are 1, right? So it's pretty much that simple. There's no or exclusivity involved. And then if this one is 1 but this one is 0, that is an exclusive OR, right? One or the other is 1 and it's exclusively 1, right? So there's a difference between them. And then the same here, right? Just the other way around. But here they're the same. So even an OR would be 1 here, right? But an exclusive OR is not 1 here because they're not exclusively 1. They're both 1, right? So this is the truth table for XOR. So basically it tells you whether two things are the same or not, right? It's like a fancy equals, right? If they're the same, you get 0. If they're different, you get 1, right? Let's go back. And then what we're doing, so that's what's going on in here, right? A XOR B, we get the difference between those things. If there's any difference, we essentially OR it with OR, right? With the letter OR there, which given my accent, I probably should have chosen a different variable name, but here we all are. And essentially what this means is if there's ever a difference between these values A and B as we iterate this loop, at some point in here, this XOR operation will return a 1, right? At some point that'll return a 1. And then it's sticky, right? We'll set that 1 then on the or variable, and it'll just stay. It'll always stay. Or is really only additive. You can, if once you set something, it's gonna stay set, right? And so, but we'll iterate over all the values. And so now, instead of return true, we just return or equals 0, right? The only way or is 0 is if every single character in both of these strings were identical, and we iterated across all of them, right? And so if I run that now, I just get gibberish, right? The timings are all gone. It just has absolutely no idea what's what anymore, right? My guesses are garbage. I don't have that anymore, let me in, or anything even closely resembling it, right? And so this is the trick. Now, unfortunately, it's not intuitive code to write, you know, and to sit down and take a cryptographic algorithm. Someone's pointing out that they still know the length, and that's true. And it is actually possible to avoid disclosing the length, and by using padding and other approaches, and we'll cover that in a bit. But the you know, the trick when you're sitting down and you're writing, you know, a complex cryptographic algorithm, that can be hard enough on its own, like just getting all the math right and turning that into code. It's then often made harder again because you have to start coding in these styles, and it's not an intuitive code style, you know. And when you do it, you know, we have examples of it in S2N, our open source TLS implementation. Like, I highly recommend extremely liberal code commenting to explain this crazy stuff and what's going on to mortals, so that they can follow it, right? So that was pretty cool. We actually saw a side tunnel action. We were able to mitigate it. It's pretty cool. So we're gonna work up from there now, and we're gonna do slightly more advanced kind of code level side channels and system level side channels that rely on shared things, right, and how they work. And we're going to kind of glue everything we learned in the last, like, whatever it is, 40 minutes together to make all that happen. So the point of everything that I'm about to go into, right, I'm going to cover a really simple example of a shared cache side channel, right? And it's not going to involve CPUs at all. Actually, I'm going to use CDNs. So if you don't know what a CDN is, it's a content distribution network, right? And the way content distribution networks work is, you know, you've typically got an origin, and that's like the customer's website or your website or whatever, right? And then the CDN sits all over the world. They've got these things called POPs. And the magic of a CDN is, you know, your users, their requests are sent to the closest POP, right? So they get super low latency, and ideally the content is served out of a cache, so they just get a really fast, snappy result. And then these POPs, you know, whenever the entry's not in the cache, you know, they can go ask the origin for the data, right? And then keep it in the cache, right? So we've got a cache here. How can I use that to, you know, implement some side channels, right? Well, one way is imagine you're able to see or kind of statistically profile when a cache is empty, right? Like, and one way to do that is to just send requests, right? So if you send a request to a cache and it takes a long time to service that cache, you can guess, well, that item probably wasn't in the cache, right? And if it takes a very short amount of time, you can tell it was in the cache, right? And so let's say you're Eve and you're spying on someone and you see somebody make a request to a CDN and you want to know, well, what were they just downloading? What were they looking at? I want to know, right? Well, you can make a request for some items you consider likely suspects or suspicious items or maybe illegal items yourself, right? And if they come back fast, well, now you know, well, it's possible Eve requested that because, you know, it's in the cache. But if it's if it took a long time, you can kind of say, well, Eve probably didn't request that. Probably wasn't it. It wasn't that, right? So you can kind of do this active exclusion, right? And by looking at like, the nodes Eve goes to, and you can eventually produce this kind of unique fingerprint of the actual nodes that Eve spoke to, right? And then you can hit them each with like your trial requests to see what the content was, and maybe those requests are for like different items on a web page. One's an image, one's a CSS, whatever. You can eventually kind of figure out and make a pretty good guess at what it was Eve was looking at, right? Just because you're measuring the return time in the shared cache. It's because you can access the cache just like Eve did, right? There's all sorts of other practical limitations, like trying to actually do these attacks in the real world. But it's just a really simple example of how, well, if you share a cache, you can start measuring these things and you can figure these things out, right? So other systems, or a lot of systems with caches like that, tend to have to, they tend to partition the caches and make sure people can't just share things and avoid all these things. I'm seeing comments like this wouldn't work for any cache, but you can get around any cache trivially. It's pretty easy to come out whatever nodes you want and do all sorts of controlled network ingress and so on. So this is a simple example of a cache. I want to cover the CPU cache case now that we just have this kind of background, right? So in CPU caching or other microarchitectural side channel issues, things can arise when different security contexts or different execution contexts share a cache, just like we saw there, right? We can, and the way to think about a CPU cache, or the way I think about it at least, right, is you've got like all your main memory, right, which is laid out on physical DIMMs plugged somewhere in a board and so on, right? And then you've got several, and it's kind of slow. I mean, it's nowhere near as slow as disk, but it's slow, or but it's still pretty slow compared to the execution time of a CPU. If every operation that happens in a CPU had to go to main memory, it would be incredibly sluggish. So there's levels of progressively faster and faster caches that are built into CPUs. Typically, you've got a last level cache, or LLC, sometimes called an L3. That tends to be something that's shared at a socket level, like a whole CPU socket will have those. Then at core level, you've got L2s and L1s. And these, I'm not doing a great job of drawing them, but they actually get smaller in size, but also faster. Just the types of memory and transistors they're built from at each point, right? And if you're sharing, especially these things, between execution contexts, people have come up with interesting attacks and bad things that can happen, right? So I'll cover a really simple example. We'll cover either like maybe a prime probe or a flush reload style side channel, which is so the data in these caches is laid out in 64-byte chunks or sometimes 128-byte chunks, which are called lines, right? They're just cache lines, right? And so imagine you're running on a CPU and you just go and fill cache lines with known data, right? Like, your data, you just put it in there and so on. So this is called priming. You're just priming the cache. You're putting stuff in there, right? And then you go away and you let some other stuff happen. And let's say somebody else runs code on the same CPU core, right? Okay, let them go run it. System lets them do that. But then control comes back to you. And then you just go walk the cache and you see, okay, I'm going to make a memory lookup for A, B, C, D, E, F, right? I'm going to measure how long each one takes to respond. And if A comes back fast, okay, that was in the cache. But if B comes back slow, the cache line was empty for you, and the system had to load that data back from main memory or the L2 or the LLC or whatever, all the way back into that cache line, right? So that's how that was accessed. Now okay, well, while execution control was gone away, they accessed something which was stored at this cache line. Okay. So that doesn't sound very useful, right? That's about all you can infer. There's other techniques, like I mentioned, flush, reload, and so on. But essentially what you're getting is the layout of where something was accessed, right? Not what was accessed. You don't get to see what data they actually stored in that cache. All you can tell is that they used they stored something in that cache line. Your data got evicted and had to be pulled back in the next time, right? Now, how is that interesting? How can that be used? Well, modern, the way cryptography works, right? Generally, you're doing operations with huge numbers. Like, an RSA key these days is, typically, 4K, right? So like 4096 bits, or an ECDSA key, or an ED25519 key. All these things are like very, very large things, and when you're dealing with these numbers and doing arithmetic with these numbers, they don't fit in a CPU register, right? They're not native numbers that you can run on a CPU, like you can add or divide or multiply, whatever. So you got to use like big num math and big num libraries to do things. And the way those work, right? Like, they do old school multiplication and division like you learned at school, right? But on these really big numbers that are laid out in memory, right? Like the product of two 4K numbers, right? It's really, really big. And that's just laid out in memory all across those cache lines, right? The same way. And it's in order, the leftmost bits are in one location and the rightmost bits are in another location, and so on. And if you know the address layout of the program that's using the keys and so on, you can figure out like which cache lines certain parts of these numbers will land on, right? You can figure out where they land on. And then if the arithmetic is not done using very strict like constant time programming like we looked at earlier, right? If it's just done in the kind of straightforward, naive way, you can figure out, okay, well, when they did multiplication or division, they touched this line, and then they touched this line, and then they touched that line, and so on, right? And that's enough information to let you start to guess what the key is, right? Because those offsets correspond to values of bit positions in the key, right? You can start to figure out what the key is. Now, so that's how they work. That's what's going on, right? It's not that sophisticated. It's actually really, really simple. Now, obviously, at a code level, the mitigation against this is just write the whole thing in constant time. Our own big num libraries are written like that. My colleague John Harrison has written a really cool one that's all constant time the whole way through. And so you avoid that. At a system level, don't share these caches is another one. So for example, EC2, like we just don't share these caches between tenants or virtual machines that are running on the same physical hardware. We actually take huge precautions. Same is true for Lambda. One of the reasons we use virtual machines as our big security boundary for different security contexts is because it gives us these controlled points where we can coordinate with the CPU and we can say, okay, we're about to switch this core from this tenant to a different tenant. Let's completely clear the cache. Let's completely evict everything. Let's use clever cache partitioning so that they don't ever share lines at other levels and so on. And that's a useful thing at the system level too. But the primary defense is that these cryptographic routines and so on just do it in constant time. Now, these side channels can be much harder to measure than the ones we've covered so far. The signal to noise rate you're getting is low. You saw earlier when I ran my password cracker on my machine that just like a few bytes in, it was starting to get infected by noise because I'm running Twitch right now on the same piece of hardware and my CPU is getting a little hogged and so on, right? But you can imagine on a system that's busy, that isn't quiescent, you're not going to get a very clean signal. It's going to be very, very noisy, and that's going to increase by a huge number the amount of measurements you actually need to do anything, which is kind of contradictory, right? Because if you need a lot of measurements, you want the system to be busy, right? You want to have a lot of opportunities to measure. So never seen a practical real-world attack based on these issues. Never heard of or seen any evidence of anything like that. So maybe they're just impractical for those reasons. Of course, we should all be paranoid and still stay very well protected against them. But it's the job is very, very hard. The other thing that's interesting is, if things get harder the higher up you go, right? You've got, L1s are super, super fast, and if something gets evicted from an L1, you can measure that quite quickly. L2s are slower, so the kind of signal rate is slower there too. LLCs, the signal rate is so slow, it's probably completely impractical. And main memory, you're into other kinds of side channels if you want to even think about it. Things like rowhammer and so on, which, we and others have other protections against. Things like ECC memory and so on help you out there. But it's still cool. It's still super interesting. This is what's going on. Now, what has become more practical and more interesting are speculative execution side channels, right? And they play a slightly different game. So, as a CPU is going through code, right? One of the optimizations CPU vendors or some CPU vendors have done is to go, well, we're actually going to do our processing out of order sometimes, right? We're gonna sometimes, we can see that there's this branch coming up, and we could go to the left or the right, and we could do A or B, right? And internally, B might also have another branch that, goes to C or D and so on, right? And it can go, well, I don't know that I'm going to have to go down B or C or D yet because I haven't evaluated that branch and I don't know what the data value is that I'm going to look at. But I can speculate and I can just go try it. And I can just go run the code. And if I don't ever get to branch B, I'll just throw the results away. Don't eat them. It's like it never even happened. It's like a tree fell in a forest, no one was around. But if I do end up going down B, I already know the results, right? My speculation paid off, right? That's speculative execution in a nutshell. And the trick is sometimes speculative execution can cause, things to be loaded into caches based on a value, right? Because that's what was in the branch. And so sometimes, and by observing whether the speculative execution actually ends up paying off or not, which you can time, you can tell what the value was, right? Essentially, I'm giving you the slightly simplified version so we can follow along here. Which is why we and others, go to extreme lengths, and we work with those CPU vendors to make sure that we're flushing all of the state and all of the speculative execution state too, and anything at all that could potentially reveal data to completely lock down issues like that. But it's also an issue that also those kinds of issues you got to fix at the code level. All right, so we've actually gotten through pretty much almost everything I had to say about side channels, but I wanted to leave one thing to the end, which is that every time I cover side channels and I start talking, I show that example of a password cracker, or we talk about length and so on. People ask, okay, why can't I just add noise? Won't that defeat it? Like, won't that work? Won't that prevent these issues? So if we, yes and no is the answer. And I'm going to cover, because it's not intuitive, but it's worth understanding what's going on. Why I give that answer, right? So earlier, right, when we did the password cracker, we essentially, we try every single, we try every single letter, and some of them take a short amount of time, some of them will take a long amount of time, and so on, right? And so that one sticks out, and it's wrong. So we know it's the one. Now, suppose we add noise to all this, right? Let me get a different color. So let's say we add a variable amount of noise, right? Well, you can probably see the problem straight away. So let's say this noise varies by different amounts, right? You're still gonna be able to tell, right? Just by making more measurements. Right, and so we're going to zoom in on a good example and a bad example. So we're gonna zoom in on C where the letter was guessed correctly, and so it took slightly longer, and B where it didn't. And so we're gonna and see, well, from an attacker's perspective, if I was measuring both these things, how would I be able to tell what was going on, right? So let's say I add some random noise, right? And in the B case, the values I measure end up being this one. And in the C case, the values end up being this one. So if they're in this region where they overlap, right? I can't tell whether it was B or C because they overlap. And it could have been either. But if it's in this region, I can tell it was B. And if it's in this region, I can tell it was C. Right? And so just by doing, and it's a two-tail, there's two tails to this. I get both ends of this. Now, you might think, okay, so I'm adding, I didn't say it, but here I'm adding a uniform noise. I'm saying all the noise I add, like some kind of artificial delay, I'm going to pick the value as a uniformly random value, right? So, a uniform distribution, if I did some kind of scatter plot, just the points are everywhere with equal likelihood, right? If you're going to do some kind of stateless noise addition, a uniform random distribution is the best, absolute best you can do. Now, sometimes folks think, well, if I make my noise a very clever shape, if I make it like log normal or some kind of peaky value or something, then I'll make it even harder. It actually never works out because once you do that, like, let's say I make it some kind of shape to it like this, the trouble is, let me get a different color. So there's my first scatter plot, and there's my second one. Sorry, I didn't realize it was on that screen. The trouble is there ends up being even less overlap, no matter what way you do it. And there just becomes more points at which you can discern the two distributions, right? So like everything in here, is green. Let's say that's the B case, and everything in here, is red, and that's the C case. And so you just end up with more opportunities to discern between the two with that kind of a shape. And it works for any shape that isn't a uniform. The best you can do is a uniform distribution like this. If you do a uniform distribution, you're increasing attacker difficulty by a square power, right? So you're basically making them have to do a square powered number of operations to work backwards and figure out whether it was B or C. And that's a square power of the fidelity of the noise, right? So the noise has to have more fidelity, has to be more granular than the original timing signal. So for example, if the difference between these two is 10 microseconds, right? Well, if you add noise in 50 microsecond increments, it does nothing, right? Because they'll still be able to tell. They'll be able to say, well, this one was 60 and this one was 50. So clearly that was B and that was C, right? So the noise has to have more fidelity than the signal. So you have to add, so if the original signal is 10 microseconds, the noise you're adding, you'd really want it to be like, say, nanoseconds or something like that, or femtoseconds, something really, really, really small. And whatever that fidelity is, whatever the range of noise is relative to the original signal, right? So let's say you've got 10 microseconds of signal, and let's say you add, let's say, nanoseconds of noise. Let's say you add, I don't know, like 1 billion nanoseconds of noise, right? So a full second, which is like, 10 to the 5 times bigger than 10 microseconds. You're going to increase the attacker difficulty by a factor of 1 billion squared, right? Which is a huge number. You're starting to get into cryptographically large numbers. So that's why I say yes. If you get the fidelity low enough, and if you make the noise spread big enough, you can actually use noise to defeat attackers. It will work. It will get you to cryptographically large numbers. We do this. So in our S2N library, anytime there's an error case, we add up to 30 seconds of noise. We add between 10 and 30 seconds of noise. So there's a 20-second window of noise, granular to nanoseconds. So we just add a huge amount of noise, and we don't even think there are any side channels in S2N. We've gone and eliminated any, but just in case, we still go and add the noise, right? Huge factors. Now we always add a minimum of 10 just to frustrate any potential attackers. They always have to wait 10 seconds just to do a measurement, and then we add the huge spread of noise just to defeat any potential timing. We actually screwed it up the first time we implemented it. We only our noise wasn't granular enough, and there's a great paper published called Lucky Microseconds, where the authors of the Lucky 13 paper found that the noise we were adding actually wasn't granular enough, and ended up only increasing attacker difficulty by a factor of 83 million, which is significant and would prevent real world attacks in my opinion, but is not, it's not cryptographically large, so it wasn't as effective. My colleague Mark Brooker made a great observation from he did his PhD research on like radar and like really cool stuff, and he made an observation that you can actually do better than uniformly random, sort of, if you're willing to keep state. If you're willing to keep state, what you can do is you can make sure the spread is random. You can say, okay, well, I picked this one, so I'm not going to pick it again, ever, until I've cycled through every other possible value, right? And that will actually do better than average, which is which is pretty cool. And I did the math on that, and that gets you like an extra square power. So it's like squared, right? So it's it gets you way up there. So that's why adding noise doesn't work, right? Because if you can do these repeated measurements, and so when we're doing or that if you want it to work, you have to think through those details and be really clever. If you're looking at lengths, like content lengths, noise is not the most effective way, right? Now you could add a random amount of noise to the end, but again, if like someone can observe the same file over and over and over or whatever, they're going to be able to eventually subtract that noise and just get rid of it. So the standard answer for hiding length is to pad to kind of a fixed interval, right? Some like military grade encryption does this. They only send data, basically the wire is 100% all the time. They're always sending data at line rate. Every frame is completely full, and you can't tell what's going on inside it, right? Which is really cool. TLS has padding, and you can pad records up to a fixed size too. And if you pad everything to roughly the same size, you're hiding everything in the noise. There's a great format I love. There's a great paper called PERBS, which is about how we bring privacy to encrypting things like binaries and text files and data and so on. And they have a padding scheme that I really like that basically rounds everything up to like the nearest log power, basically. And kind of buckets all sorts of pieces of content into the same size, and so you can't tell what's what anymore. And I wish there was more of that in the world. I wish that was kind of something that was pervasively applied in a bunch of places. We do it in some, but I've never really seen it out there in a practical application. But padding up to a fixed size is the way to go if you're trying to defeat length analysis and most traffic analysis. Anyway, that was everything I had to cover. And I'm going to take the opportunity to scan through the questions, and we'll see how we do. For those who have joined, I mentioned at the beginning, all this is going to end up on YouTube, so you can watch at your leisure. All right. Scrolled all the way back now. Oh wow. I didn't. Last time I wore a Buchanan tartan. I'm from Ireland. We do have tartans, but I don't know anything about tartan. Except once I was in a band playing Cape Breton music, and we had to wear Cape Breton tartans. So that time I knew what tartan I was wearing, but in general, I don't know anything. All right. Oh, yeah. There's a great comment in here about web servers detecting whether they're being called by curl, which is a kind of a side channel, right? Like curl is just by the patterns of its I/O is basically leaking a client fingerprint, and the web server can give it different data, which is super interesting. It enables that scary attack where, like, you look at you curl something and you it looks safe to you. You know, you read the shell script and it's like, oh, it's not doing anything unsafe. And then you do curl pipe bash and then it does something evil. And they just detected that it was piped based on the back pressure and the rate it's reading from the web server, which is mind blowing. It's really, really cool. I saw Jeff make an observation that people can sometimes deliberately try to use side channels, right, to communicate between things. There's all sorts of papers published on that. It's way easier to generally, you know, when you've got two sides cooperating and you can deliberately make systems quiet at certain times and so on, obviously it's way easier to get data across. And there's, you know, examples of people doing that on networks and so on. It's super interesting. There's a conversation about encryption and compression. Just again, for everybody there, you cannot compress encrypted data. So in general, you have to compress it first and then encrypt it. And to avoid compression side channels, you have to make sure that the input contexts of your compression kind of rounds are separated, and that you don't ever compress attacker-controlled, untrusted input with sensitive input. Don't ever mix those, right? Cool. Did I need to write the equality check myself because the Rust standard library compares word by word? Yes. So under the hood, Rust compiles down and uses, you know, a standard memcomp, which does it word by word on the processor, then finds the first word where there's a mismatch and then does what's called scrolling inside the word to figure out where the difference is inside that word, which makes your life harder. You can still defeat word by word stuff. It just takes a little more work. And there's a whole kind of arena of really advanced side channel techniques where what you do is you force the data to move around to like interesting windows. So if you're trying to focus on some like a particular byte of data, maybe you move it to like right at the boundary between two pages, right? Or two cache lines or two words, right? And just by measuring different behaviors, you can tell which word or page or whatever or cache line it's in. And then you can try to reverse, or you can try to work backwards from there and learn interesting information too. And there have been real world attacks research that, you know, has figured out how to do things like that, which are super cool. There are acoustic side channels, F. Flannery notes, which is true. You can there's people who've, you know, figured out what people are typing just based on recording the audio of the keystrokes, which is kind of amazing. There we go. Jeff Barrett talks about putting the password across a page boundary to watch when the page fault occurs, which is exactly that. That's a way to do it. Someone makes a point that compilers and optimizers can be our enemy here, right? Because I can write this beautiful constant time code, and then the compiler can try to be really smart and come along and go, you don't need these crazy XORs. This is equivalent to just doing a memory comparison. I'm just going to swap that in for you, you know? And, you know, I'm involved with some industry groups where, you know, we're trying to cross that barrier between folks who write cryptographic code and folks who write compilers and figure out how we can all work together and not have things like that happen. It's definitely a concern, although, again, I haven't really seen a real world issue crop up like that just yet. All right, let's see. Put the password and input in 0 buffers of known length and compare until the end of the buffer. That works. That's basically equivalent to doing the XORs. Doesn't work for other cryptographic techniques, but definitely works. And question at the end, why are perps better? Well, because they pad everything to a known fixed size. All right. Thanks everybody for sticking with me. This will be up on Twitch for whatever it is, 16 days. I'm going to get the other videos up onto YouTube pretty soon. If you have any other feedback or questions or suggestions for other things I could cover, or I could get someone else to cover, let me know and I'll get on that. Always looking for suggestions. We'll see. I don't know if I'll run that poll again or if I'll just run through the 3 things that were in that poll in order. But thanks everybody, and have a good rest of your Friday. Bye.